Welcome back to Nerding Out About Software. Today I want to talk about Goroutines, Coroutines, and in general asynchronous I/O operations, how different languages do them, what the implications are of those different implementations based on what's happening under the hood, and how you would think about them when designing your own systems around them. We will first look at Go, which is the big language that everyone knows is designed to be good at this sort of operation. We'll compare it to C++20 coroutines, which are a different, more old-school approach to the same problem. We'll also have a quick look at Python's async I/O and see the simplicity in there and talk about the trade-offs you get for that simplicity. And at the end, I will show you a simple example in Odin of how you would build this sort of coroutines behavior in a language that does not have async await natively in its standard library. But first, let's explain what actually happens when you execute functions, when your program does things, when system calls are executed. So your traditional setup is single-threaded. You do one thing, once the thing has finished, you do the next thing. That's your procedural programming 101. Now, this isn't necessarily perfect because different tasks can take different amounts of time, and when you enter the web world and I/O, you can sometimes be waiting for an endpoint to return something. You could be calling out and awaiting a response, and you don't know how long it will take, and you could be waiting for one of them to finish before you even start the next one. So the idea of async is that on one lane you take many turns where you start calling out, bring me this data, for example, and then you suspend that, get onto the next thing. That thing can start doing its own thing, then you will return back to the first one and you will periodically check all of them and see when they finish. So that's sort of the core idea, the conceptual side of it. So that's great. That's how we first started doing concurrency before we had multiple threads and processes. When we added threads, well, you can run three things at once when you have three threads and so on and so forth. So that's your sequential threading. You just like, on this thread I will run this and this, on the next thread I will run this and that. The cool thing happens when you have multiple threads and your async formalism, because you can have different threads check on different things at different times, and it becomes this sort of patchwork of checking in on your processes happening in real time. And now let's look at the specifics of how different languages have implemented this in practice, because the core idea is simple, but different implementations have different approaches to actually doing this. But before we do, if you enjoy this style of content where I'm talking about random ideas in software and showing you some examples, like, subscribe for more, and let me know in the comments what you would like to hear more about. Now let's talk about the Go implementation of doing async I/O with the Goroutines. The Goroutines are a GMP model where you have many Gs, your Goroutines, your tasks, that are being managed by fewer logical processes and OS threads. Very interesting how they've done it, because every single Goroutine, each one of your tasks, get its own dedicated stack allocated on the heap, as opposed to the other languages we'll look at today, which use the OS thread stack and just have a defined frame of when you can suspend, what variables have to be passed around, and so on. In this case, you get an actual dedicated stack for every single Goroutine. The stack itself starts very small at around 2 kilobytes, but it can grow in size over time. That's the difference between having a proper stack and having just a frame that defines things. The implication of that is if your stack overflows, it will essentially double in size. That's the easiest trick in the book. If you've ever written a dynamic array in C, you will know that the simplest approach is like, oh, if I overflow, double the size. So the runtime does it for you. It will increase the size, rearrange all the pointers, everything is seamless, and it can grow to gigabytes, which is why it's really good for light operations like I/O, because your stack won't get ridiculously large, but it can grow to gigabytes. So for heavy compute, you might need to watch how you're designing your system around this. But it has a very, very gigantic benefit, and that benefit is the stack can be suspended at virtually any point in the operation. You do not have to define at which spot you have to wait, at which point you have to suspend, and so on. All you do is write your normal code and let the runtime handle it for you. So in this situation, the runtime does all the work. The Go runtime just handles all the size changes, all the pointer rearranging, all the suspensions, and arranges it how it wants to. Which is the opposite of other approaches where the compiler does all the work, and the programmer, you, designing your system. Looking at a code example of actually doing Goroutines in practice, it is moderately simple. This is a very toy example that we'll be doing. We won't be doing complicated I/O. We will essentially fake reaching to some URL, waiting for it for 100 milliseconds and getting something back. So we've got our set of URLs, which could be thousands of them, and usually would be. We will prepare our results. We create a wait group because, well, in order to do async, it's not just that you send things out and start them, but you also need to wait for them to finish. So that's how we will know, oh, we need to be waiting for this. So for each of the URLs, we will add a thing to our wait group, and we run a function using the go keyword. So the go keyword tells the compiler in the runtime, this is a go routine, this will be run on those little stacks. We defer the wait group being done and add the result to our results. It is very simple syntax. All you need to do is prepare your group, add things to the group and send the go routines, and then defer the group being done. Again, the defer keyword just takes whatever you put after the defer and puts it at the end of your scope. Relatively simple, even though a lot of things happen behind the scenes. There's a lot of things happening to those stacks, and the runtime really does a lot of work to do it. The actual code is very simple. In comparison, C++ does it quite a bit differently. So instead of allocating a growable stack that can contain many functions and basically a full execution block, you only allocate one frame per function on the heap. So you define your state, your local variables to the function, and the behavior for when it can suspend and when it can resume, and that's it. There is no huge runtime overhead because you've defined everything properly. The compiler does all the work for you. That means it won't grow in size. So once you've allocated it, it will be pretty much that size. And also, it is not suspendable whenever you want. You can't just suspend anywhere within the function because you can't suspend the whole stack like you do in Go. You need to define every single spot where it can suspend and when it should resume, which is a slightly different paradigm, but it does the same thing. The small quirk with C++ though is that you need to bring your own executor. It doesn't contain one in the standard library. In the real world, you will use something like libunifx or boost ASIO. There's tons of implementations everywhere, as it is usually with C++. There's always a solution somewhere. Or you can just write your own if there is something very specific to your implementation that you need. Looking at the code, for now skipping the actual task executor, which is the complicated part, doing the implementation is not too dissimilar from Go in some ways. Our task will be exactly the same. We will just pretend to receive something. We'll sleep for 100 milliseconds and return the result. In our main function, we define our vector of URLs, we will define our vector of tasks, and we will reserve the proper amount of size. That's the thing. You need to manage your memory manually in C++, so we do need to care about this. So we need to do those reserves, but then it is sort of the same behavior. We just iterate over them with pushbacks, and in a while loop check while remaining yield from those threads. Now the task executor, this is more for fun than to actually talk through it in too much detail. I put together a very simple one in a C++ module because modules are here and we should be using them. We should not be writing header files if we don't need to. If you need to write a header file, you know why. But all we need to do is define our task as a struct with a promise. So we define specifically what's going to happen. We define our initial and final suspends with no excepts, and we return our values. Naturally, we will need to set out our destructors. This is C++ after all, but the actual task is not too complicated. We just define what it's going to do, when it can suspend, and that it should terminate when something goes wrong, and that it should destroy and free memory if it's no longer in use. And of course, since we are sleeping, since we are suspending things, we need a sort of sleep structure or sleep function. Quite a bit of work, but it is not conceptually too difficult to grasp. But what about something even simpler conceptually? How does Python do it? Well, Python is a very commonly used language these days, pretty much almost as common as TypeScript is. How does it do it? Well, we only deal with one thread for async IO in Python. So we no longer have this split between different threads. It's a lot easier in that regard. All we're doing is the most classic async scenario of awaiting, suspending our tasks. So we have one OS thread held by the global interpreter lock. We have our little event loop from async.io, and we have frames. So those frames are exactly the same as they were with C++. Well, exactly. They are of the same style. The actual difference is every single thing, every function, every frame are full Python classes with all the possible pointers, reference counting, and so on and so forth. So that overhead becomes quite large. So for every single task, you are actually allocating quite a bit of memory. So we were talking about Go with about 2 kilobytes per stack, and that's an actual fully executable stack. Then with C++, we have very small frames. They are absolutely tiny. You can pack them as much as you need. You define the size. Whereas in Python, every one you spawn will be at least of hundreds of bytes, usually quite a lot more. There is no way around it. That's how the CPython works. Everything you do will be a CPython allocated thing. But the beauty of it is simple. You trade the RAM usage and the performance of everything for simplicity. And for the most part, if you're running a strong enough machine, you don't actually care about those little losses of performance. I usually do, but in the real world, you just need to ship fast. That's where Python absolutely shines every time. Looking at a very, very simple example of async.io for the same toy project of just fetching some URLs with a fake sleep. Our fetch is exactly the same as it was, except it's defined in seconds, not milliseconds. And then all we have to do is results await async.io gather. So we just do our fetches, tell async.io, listen, you'll be awaiting getting this, and that's basically it. Async.io run your main, and that solves it. There is though a little bit to worry about, namely you have async everywhere. You need to define your awaits. That makes sense because whenever you send something out, you need to await it coming back. But the async propagates all the way through the graph. So your main function has to become async. Your main function is executed by async.io. Everything needs to handle those async paradigms. And that's something that's quite natural with stackless implementations. You will end up having to propagate that asyncness through everything. The same thing will happen in Rust, though async Rust is complicated enough that it would deserve its own video rather than trying to put it in here, unless you just use Tokyo and have it macro everything for you. With Go's implementation, you don't have to propagate asynchronous everywhere because, as I said, the runtime does it for you, and every task you run is just a stack that is fully executable and fully suspendable at any point. And that's the main difference between them. But let's dig deeper into what's actually happening and write our own Coroutines implementation from scratch. So how do we go about designing a Coroutines style behavior? Well, we think of what we've been doing so far. So first thing, we have our task, which in C++ and Python was allocated on the heap as a frame. So that's what we're going to do. We're going to define a struct, which we will allocate on the heap. All we need to do is have some parameters, like in this case, the URLs we were fetching, some results, because we need to return some value. We'll have the state, so we know where we can resume, and we'll have some kind of local time variable that tells you how long till the wake happens. Now, once we've defined those frames, what is the loop? How does stuff behave? So we start our IO, we set when we're going to look at it again, we wait for it, and we keep polling to find out, are you ready yet? Are you done yet? Once all of it is done, we have a finish, we're done. That's how we're going to execute it. It's not actually conceptually difficult. You're simply just starting something, setting a timer, okay, how often should I look back at it? Is it still happening? And then checking in. When you get a result, awesome, it's done, carry on. You can sort of feel analogously if you deal with AWS and you do batch jobs, when you do deferrable jobs where you send something off to be done on the batch system and you periodically check, is it done yet, and pull some data back, just finding some logs or stuff like that. This is the same sort of behavior. So you can just set thousands of jobs running, look at them every 10, 30 seconds, however often you like, And that way you're not paying the runtime cost of checking constantly and streaming constantly what's happening in the batch system. This is exactly the same behavior except distributed across computers. Now, if we set up our event loop properly, we will have multiple tasks that will take steps, and we will take a step of each task. Once we've done that step, suspend it, go to the next task, go to the next task, and so on. Our loop will iterate, revisit each task with every loop. Simple enough conceptually. So let's see what a code example would look like. So looking at a code example, we have quite a lot more to go through because we're writing every part of it from scratch, but none of it is particularly complicated. We start with a state machine because we need to know in what state our task is. Is the task done? Is the task not done? We define our state machine with just start, waiting, and done for this simple example. That's where enums shine. Gladly, Odin has a great enum support. Then we define our task struct, in which, as shown in the diagram, we just have URL, result, state, and some time for wake. Then we create a function for a step, like one slice of the execution, like we will be checking in and looking at stuff. So this step procedure, we just have what will happen in every possible state. So if the case is start, if the state is start, we will do starting fetch, wake me after this time, change the state to waiting IO. When the case is waiting IO, when the state has changed to that, next time you check, oh, it's at waiting, we will see, has it completed? If it has completed, we get the result and change the state to done. Once the state is done, we just change the boolean of whether this task is still going or not. You see that all we're doing is checking what's the state. If it's still going, give some information, maybe change the state, carry on returning that it still should be going. Then once it's done, it returns that it should no longer be going. You can yield all the information. That's the entire idea. Now our event loop will be exceedingly simple. It's just for all our tasks checking, is it alive? Are any of them alive? So we will iterate over our tasks, take the steps, see, are you done? If yes, awesome. If not, carry on, we'll keep checking. And then in the main procedure, we just execute all of that. So again, it's not actually difficult. And the difficult part is how you allocate that memory and whether you want to go with a stackful or a stackless approach. And that's why different languages have different implementations of it, because for different scenarios, you need different things. In languages like Odin, where you don't have a native async await, it's less than 100 lines of code to write something that will do this form of behavior. It will not be generic. Like this will be specific to our task that we've defined. These are specific sleep points. Languages that have async await behavior built into the standard library will have predefined ways of handling when those suspense should be and all of the built-in syntax and so on. But the core idea is not actually complicated, and you can build it yourself. So hopefully you enjoyed this little dive into how async is done in the real world. If you have thoughts, leave them in the comments. Leave a like, subscribe if you want more, and if you have ideas for future videos, let me know. I thank you so much for your attention.